Okay, so this is going to be the third way to find volume. So the first way was discs. Okay, so discs are cylinders, but we're calling them discs. The second way was washers, which discs and washers are a very similar method because they're both using the volume of a cylinder. Basically, it's just whether it's a hollow cylinder creating a washer or just a regular cylinder, which we're calling a disc. Okay, this time it's called volume using cylindrical shells, and this is going to be very different. We're going to be finding the volume by basically looking at a bunch of shells right next to each other. Okay, so you can see like this is looking at, right here, this is looking at one shell. There would be an infinite number of these. This is where this is most comparable to a roll of toilet paper. Each wrap of the toilet paper is its own shell, and you're going to be adding up an infinite number of shells. Okay, toilet paper reference in this day is kind of funny. But okay, then over here, this picture is another time where you can see all these different shells that are just wrapped around. Okay, I have an image, a little graphic of this, hopefully loading. This is a YouTube video embedded in my notes, so I'm hoping it works. Okay, so this green shell right here, that's one shell. We'll add up that and then add it to the blue and the orange and the purple. Okay, so they're showing how this graph, I don't know, maybe it's, yeah, it kind of looks like it's a downward facing parabola. So that would be the bounded area. They're going to revolve it around the y-axis, and so that's going to kind of create like the overall shape is going to be like a bundt cake all the way around. Okay, but it's just showing one individual shell. There's one shell. And then let's see, what else is it going to do? So there's an infinite number of rectangles. Obviously, they're just showing like 7 of them, but just to make a good visual, so that would be like half of the bundt cake that they're wrapping around the y-axis. Showing all the different shells there. I was hoping it would just show how, okay, this is what the actual three-dimensional shape looks like, which looks like a bundt cake, right? It's making me hungry. Okay. Okay, so a few things now. I want you to, okay, there. I would like you to pause, and this link is also in Power School Learning. I want you to click on this link, and I want you to watch Sal Khan go through this. Okay, now that you've watched Sal Khan kind of talk about shells, I want you to realize that instead of adding up an infinite number of discs or an infinite number of washers, it is going to be an infinite number of shells. Thought I had my pen selected. Shells, these cylindrical shells. Okay. Now, shells. Okay, here's the big idea with shells. Well, for shells, we're actually going to talk about the individual. So to find volume, we are going to actually find the surface area of an individual shell. So the surface area of an individual shell is what I would imagine taking a piece of paper and just rolling it, okay, so that you have a circle. And that paper has a surface area, right? So the volume is actually going to be whatever the surface area of that individual shell is times, to get volume then, is like the thickness of the paper, which we want to be infinitely thin, right? Okay, well, the surface area of a cylinder, okay, is, I always demonstrate this in class, but the surface area of a cylinder is basically a rectangle, right? If you were not considering the two circles, the circle at the top and the circle at the bottom, that's not what I'm talking about. I'm talking about, the actual can part of the pop can that you grip. Okay, if you were to cut that, you could lay it flat and it makes a rectangle. And that area of the rectangle, the longer part, is actually just the circumference of the circle. So it's 2 pi r, which is the circumference, 2 pi r, and then times the height. Okay, that's just the surface area. And then the thickness is going to be either dx or dy. Okay, and obviously when we integrate that, we're going to be able to move the 2 pi out front, and then it's just going to be the radius and the height of that shell that we actually have to integrate, and then dx or dy. Okay, a few things about shells. So I have this saying, this is actually not mine, this is Miss Drever's, but shells are parallel. This means that unlike with discs and washers, the reference rectangle is going to be parallel to the axis of rotation. So I'm going to go back here. So what do I mean by reference rectangle? Each of these is a reference rectangle. Now, when we did discs, we would rotate that around the x-axis. It was perpendicular to the axis of rotation, but you can see this one, they're actually rotating this around the y-axis, and that reference rectangle is parallel to the y-axis. So when you're doing shells, your reference rectangle here, it's also right here, you can see it's parallel to the y-axis. Shells are parallel. Your reference rectangle is going to be parallel to the axis you're rotating it around. So that means if you are rotating around the x-axis, you're actually going to do dy. And if you're rotating around the y-axis, you're going to do dx. Now, this is not the same for discs, and it's not the same for washers. For discs and washers, whatever axis you were rotating around was the axis you did the integral in terms of. Now, this is totally different here. For shells, it's going to be the whatever your axis you're rotating around, it's going to be the other variable that you use. Okay, so obviously we need lots of practice and we need to talk about this more. So this is a shell. Okay, so this is a hollow, infinitely thin shell. So for this first one, it is so this is your reference rectangle right here. Okay, so here's your reference rectangle that's being rotated. Okay, it's clearly being rotated around the y-axis. Okay, we're taking that reference rectangle, rotating it around the y-axis in order to create this shell. Well, this reference rectangle, its thickness right here, its thickness is a dx. Okay. As you rotate it, you rotate it around the y-axis, but its thickness, one of the S's, I swear I drew it, thickness is a dx, which means although it's around the y-axis, everything for its volume is going to be in terms of x. Okay, so what is the volume of this individual shell? Well, the volume is whatever the surface area is times its thickness, which is dx. Okay, so that means it is 2 pi RH times dx. Okay, well, as we do this in terms of x, the radius, okay, the radius of this cylinder right here, that is the x value, whatever the x value is when you go over that rectangle amount. So it is 2 pi, the radius is x, and the height is f of x dx. Oh, that looks like a y, dx. Okay, so then over here, when you have this cylinder, here is the reference rectangle again. Okay, its thickness, this thickness right here, this guy right here, that is a change in y. Okay, but clearly it's being rotated around the x-axis. So although you're being rotated around the x-axis, your thickness is a change in y. It's parallel to the x-axis. Rotating around the x-axis, that's your shells are parallel, but your thickness is a dy, so everything's in terms of y. Okay, so I'm going to kind of write up almost the exact same thing here, but if it looks like this, if your reference rectangle is horizontal, your volume is still surface area times dy. So that's 2 pi RH times dy, which in this case is 2 pi y, okay, times, in this case, f of y, so it's got to be in terms of y, and then times dy. Okay, I am, just so, since this is getting a little long, I'm going to continue and do the examples in another video, so look for part 2.